Hey guys, this week I'm going to talk about a couple of different of these amino acid creating reactions and kind of break down some of the ones I think are a little bit less well described in the book. So I'm going to be focusing mainly on aspartate, glutamate, glutamine, alanine here, and this little serine, cysteine, glycine area here. As you can see, this is a nice little table that the book has where it kind of shows where each of these come from. So you can see that a lot of them come from either the citric acid cycle or glycolysis here. Other ones coming from pentose phosphate pathway as well as glycolysis. So you can kind of see that all of your amino acids are branching from points that you already made, which is interesting to show kind of this map that we're slowly building as we go through the course. Okay, so the first one I'm going to talk about is making glutamate. There's a couple of different ways we can make glutamate. One of them is through this glutamate dehydrogenase reaction. And essentially what happens is you have this nitrogen here is going to come in and form an imine to give you something that looks like this here, and we'll lose a proton in that process. From this point, what we're going to have happen is, so we've kicked out our water, and we're going to have this NADPH here is going to act as a hydride donor, so an H- equivalent. This will come in to reduce, and we'll end up with just an N H2. So, NH3 usually, which is also drawn right here. So this is a quick way of making glutamate from alpha ketoglutarate, which you guys have already previously seen. There's another way of doing this. Let's see if that's the next slide. Nope, okay, so I'm going to talk about that one later. The other thing is taking glutamate and turning it into glutamine. So removing one of these oxygen groups is particularly difficult to do it in a one-step process. The easiest way to do it is to use an ATP and make one of these acyl phosphates, which are shown right here. So we started off with this bad leaving group. And we've now created what would be considered a good leaving group. No, I don't want the, there we go. I'm just gonna indicate as Lg. This would be similar to having like an acyl intermediate, so if you are an acid chloride, oops. This is the biological equivalent of something like this that can easily be attacked by whatever you want. So in this case, NH2 or NH3, I guess. You would kick out a chloride in this case. Over here, we do the same thing. Oops, wrong. Stereocenter, kicking out our phosphate group, giving us glutamine in one step. So that's a quick way for going from glutamate to glutamine through a two-step process. Okay, so the book talked a little bit about PLP enzymes. I'm going to give you guys kind of a little bit more of a structural basis. You can kind of see more what's happening. So they showed this pyridoxine, which is vitamin B6. This is what you eat. What your body does is you're going to oxidize this center here to an aldehyde. and then you're going to phosphorylate at this center here. This really just is involved in binding to the enzyme active site. And the part that we really care about is this aldehyde here. This is going to essentially act as an electron sink, or something we can use to move amines from one side to another. So if we start with oxaloacetate and glutamate, which is shown up here, so we need COO minus and then COO minus here, so this is oxaloacetate plus a glutamate. So what this PLP essentially does is it allows you to transfer this amine here and this ketone here, and essentially they're going to flip. So this process is going to give us aspartate plus alpha-ketoglutarate, which is shown here. You can also do this with some other things. You can do it with pyruvate instead. So if I was to take pyruvate, and I'm just going to draw the pyruvate part this time. Let's see. Amino acids. Yeah, make it simpler. So if we instead did this with pyruvate here, this is going to go to alanine, and then the glutamate here would again go to alpha-ketoglutarate here. So it's a way of transferring an amine from one position and replacing a ketone with it. Okay. Let's see. Okay, so talking about serine. So serine, cysteine, and glycine are all made from this 3-phosphoglycerate here. The way that we do this is essentially, I'm going to talk about how you make serine and then talk about glycine and cysteine later on. So the first reaction you're doing is the opposite of what you did in the glutamate dehydrogenase. We're actually going to lose a hydride in this case. So these electrons are going to come down and kick out an H minus, which will be picked up by NADH here. Oops, looks like I've got a couple of extra string. There we go. And now we've generated this ketone. So you're oxidizing from an alcohol to a ketone in this case. We're going to do the same thing that we did in the last page. We're going to use PLP in order to transfer an NH2, or NH3 I guess, from our glutamate, making alpha-ketoglutarate, and this 3-phosphoserine here. So if you look at this, this is serine. You have the CH2OH group, but you also have this phosphate on it. So this is 3-phosphoserine. And if we lose this phosphate, we end up with just serine here. Okay, with our serine, you can either make glycine or make cysteine. To make cysteine, we're going to need another amino acid. So we're going to need methionine. Methionine is our sulfur source for cysteine, but it has this CH3 on it. And this is going to be difficult to remove just by itself. So what we need to do is form what's called SAM, or adenosylmethionine. This is an interesting reaction, as it's one of the only reactions where you actually remove both or all three of the phosphates from an ATP. From now we have this positive charge, which makes it a little bit easier to remove this CH3. So this will be a methyl transfer reaction. There are two main ones that you use in this course. They get used a lot. The other part of it, we take it from SAM and then we put it on a DNA or RNA. So let's see. So at this point, you can pretty easily pull off, because you have an S positive, this methyl group here, remove our adenosine, and now we form homocysteine. So homocysteine is a little bit different than cysteine, as you have one more carbon. So I'm going to draw out cysteine here. So as you can see, we're still one carbon longer than we want to be with homocysteine here. So to remove this, what happens is we end up doing a two-step reaction. The first one is your sulfur, and this is all enzyme mediated, from your homocysteine. It's going to come in to attack at this position, and you're going to eliminate your water, forming this cystathionine here, which is a combination of the two. And then from here, you're going to do a pretty large elimination reaction. I'm not going to go through the full mechanism of it, but essentially you're going to kick out cysteine here. So we started with serine. This is how we acquired the entire change color body of our cysteine, and then the sulfur itself is going to come from our homocysteine here. Okay, the last one I'm going to talk about is how to make glycine. So this is kind of poorly shown in this image here. So what actually happens is, and this is going to be a PLP mediated one, but I'm only going to show the structure, so this will be kind of a muted mechanism. But what happens, change the angle on that, is that you essentially eliminate this whole group here. So you'll have some proton source in solution. These electrons are going to come down, and you're going to break this carbon-carbon bond and generate two different things. So you'll make formaldehyde and glycine here. This formaldehyde, so I'll draw, is then picked up by this tetrahydrofolate. So you have two different amines that are shown here that can, well, they're shown here, and they're both able to attack, and instead of forming like a diol, which is what would happen if you had water and acid, instead, if you use these two nitrogens, you end up forming HBHs. Diamines. And that's what's going on here. You've done your addition, and they kind of highlight the individual steps down here, but you functionally make they call it a methylene equivalent, which is a CH2 equivalent. You've lost your water from your formaldehyde, but now there are two nitrogens that are bonded to it, and this can also be used in DNA synthesis later on. So you guys will learn a little bit more about where these two one carbon metabolism pathways go to in the next chapter, but from there, that's kind of how we generate a lot of these amino acids. So if you guys have any other questions, please send me an email. I hope this is informative. Have a great rest of your week.